Thank you. Hi, yeah, so I'm Ben, and today I'm going to be talking about our technique for automatically translating imperative code to functional style code using program synthesis. So this is joint work with Yanju, Yufeng, Greg, and Ishil, my colleagues at UT Austin and UC Santa Barbara. So I'm going to start the talk with a brief story. So this is Bob, the hero of our story, and he's a software developer. And Bob's boss has come to him with a job. Bob wants him to convert all of his imperative style Java code to the Java Streams API, which is a functional style streaming API. So Bob knows that this is probably important because functional style code is more declarative, so it can be more readable, it can be more efficient, and it makes it easy to parallelize code. But unfortunately, Bob has never programmed in a functional language and he doesn't know Java Streams. So he starts heading down the rabbit hole of looking up some examples. He looks up one, he looks up another one, he looks up the docs, and he can't figure it out. He's flummoxed. And luckily, he comes across our paper where we present an automated technique to perform this translation for Bob so that he can devote his brain power to more important things. Okay, so a brief roadmap of what I'm going to be talking about today. First, I'll describe the problem that we're actually solving, this translation problem. Then I'll kind of discuss in more detail the solution, so how we actually solve this problem. And finally, I'll give some evidence as to why I think that this approach is actually useful in the real world. So first, the problem. So to explain the problem, we're just going to look at a simple example. So here's an imperative style Java program. And this is a function that takes two arguments. So a string UID, which is a user ID, and a list of policies. So you can think of these as being healthcare policies. And each healthcare policy has a set of roles. And those roles can be things like a beneficiary or an owner of the policy. So what this function does is it iterates through each policy in this list of policies. And for each role in each policy, it gets the roles which actually contain this user ID and returns that information. So that's the imperative style program. Here is the Java Stream style program. So you can see it does some of the same things, but it uses functional style operators like map and filter. So the key kind of question to ask here is, why is this translation problem hard? The reason is kind of the reason that often comes up in program synthesis. It's that the search space is very large. So if we use kind of a standard enumerative technique to try to generate the stream program on the bottom, even for a somewhat conservative target grammar, we would be considering tens, if not hundreds of millions of programs. So it's not necessarily feasible here to just do some blind enumerative approach. So how can we do better? The key that we noticed is we can make some observations in this particular domain that will allow us to be more efficient in our search. So the first observation we make is that the source and target programs here share some expressions, and I've highlighted them in red here. So how can we actually take advantage of that? We introduce something that we call a cognate grammar network, which is a custom neural architecture that we've developed that takes advantage of this observation that there are shared equivalences or shared expressions and biases the search to produce programs that have these shared expressions. The second observation we make is that not only do these programs or these expressions shared across the source and target program, but they actually have a deeper semantic relationship. In particular, when we execute these programs on the same input, these expressions will take on the same values. So to get a sense of what I mean, let's consider a simple example where we have a list of policies that contains one policy, we'll call it P1. And let's assume that our policy P1 has two roles, which we'll call R1 and R2, and only the role R1 actually has this user ID in it. So let's walk through what happens when we actually execute this program. So first, when we call policy.getRoles with the policy P1, we'll end up getting the roles R1 and R2. Then when we check if the role contains the user ID, we'll get true when we execute it with the role R1 and false when we execute it with the role R2. And finally, when we call role.getName with the role R1, we'll get the string R1. So how do we take advantage of this observation? We formalize this idea as a notion that we call trace-compatibility, and we develop a pruning algorithm that prunes out programs that are provably not trace-compatible. So in the next portion of the talk, I'm going to double-click on these two kind of key innovations that we have and explain how we exploit these observations to have an efficient synthesis procedure. So first, I'm going to start by discussing our cognate grammar network, which takes advantage of our first observation. So recall our first observation was that the source and target programs have these shared expressions. And our idea here is to bias the search for target programs that contain expressions from the source program. So to take advantage of this, we formalize our observation using this notion that we call a cognate grammar that I'll explain in a second. And then we implement our idea using a cognate grammar network, which is a neural architecture. Okay, so first, what is a cognate grammar? So broadly speaking, two grammars, G1 and G2, are considered cognate according to our definition if their shared non-terminals derive the same words. So to explain what that means, I'm just going to show this simple example at the bottom. So consider these two grammars, G1 and G2. They both derive arithmetic expressions. The one on the left derives prefix notation expressions, whereas the one on the right derives infix notation expressions. They have two shared non-terminals, op and n, and if you stare at them for a second, you'll probably convince yourself that they derive the same words. So these two grammars are in fact cognate grammars. However, if we extended the grammar G2 on the right to include negative integers, but didn't extend the grammar on the left, G1, these would no longer be cognate because the shared non-terminal n no longer derives the same words. So that's the notion of cognate grammars. So what is the cognate grammar network that we use? So first, the kind of key assumption of our cognate grammar network is that our source and target programs, p sub s and p sub t, are derived from cognate grammars. Right? So what's our technique that we use in our cognate grammar to take advantage of that assumption? The technique we use is when we encounter a shared non-terminal, we assume that that can be expanded using expressions from the source program. So the goal of our cognate grammar network is to compute the following probability distribution, particularly the probability of a target program, p sub t, given the source program, p sub s. And ideally, if we compute this well, we would like to get a probability distribution that places high probability for target programs that are actually equivalent to the source program. So there's been some prior work on this. So Rabinovich et al. Presented a neural architecture called the abstract syntax network, which computes this probability by computing the probability of a target program as the product of the probability of each non-terminal expansion used to construct that target program. So this could work in our context. It would construct the desired probability distribution, but it doesn't take advantage of our key assumption, right? Which is that our source and target programs are derived from these cognate grammars. So our idea with our cognate grammar network is to extend the ASN, the abstract syntax network, from the literature with a copying mechanism, right? Where when we encounter a shared non-terminal, we compute the expansions of it not as expansions over non-terminals, but as replacements with expressions from the source program. And so you can see at the bottom, I won't go into too much detail, but this is how we actually implement the copying mechanism when we approach a shared expression. In particular, we come up with an encoding for terms in the source program, and then we learn a weight matrix W and compute a softmax. But for more information on the exact architecture we use, I encourage you to check out the paper. Okay, so that's the cognate grammar network that we use. The second key component of our algorithm is our trace-compatibility pruning. So this, if you'll recall, takes advantage of our second observation. Right, so our second observation was that these shared expressions between the source and target programs take on the same values when the programs are executed on the same inputs. And our idea here is to prune partial programs for which we can prove that no completion of that program can be equivalent to the source program and satisfy the trace compatibility assumption. So in order to formalize this, we will define our trace compatibility assumption, which is essentially our observation. And then in order to implement this pruning strategy, I'll describe our bidirectional pruning algorithm that we've developed. Okay, so first, what do we mean by trace compatibility more formally? So two programs, p sub s and p sub t, are considered trace compatible if first, for every shared term tau that appears in the target program p sub t, it also appears syntactically in the source program. And second, for any input sigma, every value that tau takes in the target program when executing p sub t on sigma, it also takes in the source program. So to give you a better sense of what trace compatibility actually means here, let's take a look at a quick and easy example. So on the left, you can see an imperative source program. So this loops over some array of integers x, and for each odd element of x, it prints out that element multiplied by 2. On the right, you can see we have a functional style program that maps each element of x to the statement print I times 2. So in this case, these are not trace compatible. And then to understand why they're not, let's consider when x is the singleton list containing 2. So the program on the left will print out nothing because 2 is not an odd number. So I times 2 will never be executed. Whereas on the right, I times 2 will be executed once and produce the value 4. So these are not trace compatible because it violates our second requirement for trace compatibility, that these values are shared. However, let's suppose we change the program on the right to replace mapping over x with mapping over odd of x, and now these would be trace compatible, and you can think about the example I just explained that would no longer occur. Okay, so that's what trace compatibility is. So now let's try to understand what our pruning algorithm does. So recall that our synthesis goal in this case is to find a target program that's in this functional style code that's equivalent to the source program. And when we say equivalent, we mean for all inputs, executing our target program on that input is going to equal executing the source program on that input. So our idea for pruning is for some partial program, piece of t prime, so some program that contains some unknowns, we want to over-approximate the possible values that any completion piece of t prime could produce on some input sigma. And in particular, we can prune a program if its over-approximation does not include the output expected from the source program for some particular input. So this is the high-level idea from our pruning, and the challenge here is how can we compute this over-approximation soundly, precisely, and efficiently? Right, and so why do we care about soundness? Well, if our over-approximation isn't sound, we might end up pruning programs that could in fact be correct, so we don't want to do that. We care about precision, because if we're not precise, we might not take advantage of all the pruning opportunities we could have. And we care about efficiency, because this is going to be executed within the synthesis loop. And so if it's very slow, even though it will help to prune large parts of the search space, it won't be helpful in practice. So how do we actually handle these things? So our algorithm uses a form of concolic execution to propagate symbolic values and concrete values to over-approximate the possible values that can be produced by a partial program. We achieve a high degree of precision by relying on our trace compatibility assumption. So in particular, our trace compatibility assumption can be used to take any shared non-terminal and over-approximate the values it can produce by considering all the values produced by shared expressions in the source program. So we can come up with a precise understanding for certain unknowns in the target program. And finally, we can compute this efficiently using a bidirectional approach that takes advantage of the inverse semantics of operators in our language that I'll explain in a second. So I think the best way to explain how our pruning algorithm works in practice is to go over an example. So here we have a partial program that's the sum of two unknowns, n1 and n2, that correspond to shared non-terminals. And the values that these shared non-terminals take on in the execution of the source program on some input are given in this box on the left. So you can see n1 takes on a bunch of even values, 2 up until 260,000, I think, and n2 does the same except for odd values. So one technique that we could use that would be sound and precise would be to take these two lists of values and compute all of the possible sums of each of the values in these two lists and compare it to the expected output. Unfortunately, as you might be able to intuit here, why this is sound and precise, it's certainly not efficient, right? So computing all these sums, there's, I think, over 60 billion sums to consider just in this simple example. So what does our technique do? Our technique takes advantage of the inverse semantics of operators in our language to reduce the search space. So what do I mean by this? So on the right, you can see kind of a simple example walking through how this would work. So in this case, suppose that for some input sigma, we know that our source program produces the output 0. And by looking at the list of values for n1, we can see that they are all greater than or equal to 2. And using the inverse semantics of our sum or plus operator, we know that n2 therefore must be less than or equal to -2. And we can quickly see that none of the values in n2 actually satisfy this constraint, and therefore we can prune the program without having to consider all 60 billion sums. Okay, so that's the high-level idea of our pruning algorithm, but I definitely encourage you to check out the paper for more technical details. So the last part of my talk, I'm going to go over the implementation we made and the evidence that I think there is that this is actually a useful technique for translating in the wild. So first, what benchmarks did we evaluate this on? So we have two benchmark sets that we developed. There is no existing benchmark set, at least that we're aware of, so both of these we collected ourselves. The first is translating imperative Java programs to the Java Streams API I mentioned before. And the second is taking imperative style Python code and translating it to the functools API, which allows functional operators like map and filter. So in total, we collected 91 benchmarks from Stack Overflow and GitHub. And at the bottom, you can see some stats about the AST size of both the imperative and functional code for both benchmarks. So you can see we're dealing with kind of medium to medium large size code, with the max here being almost 200 AST nodes. Okay, so what did the results actually look like? Here we can see the results plotted for our Java Stream benchmark. On the x-axis, we have the total time elapsed, and on the y-axis, we have the percentage of benchmarks solved within that time limit. So our tool, NGST2, is pictured in orange, the orange dotted line that you can see is well above the rest. And you can see in the 300-second timeout, it solves just below 80% of the benchmarks. We also compared to a number of other state-of-the-art tools. So in particular, we compared to the abstract syntax network that I mentioned earlier in the talk. We compared to a state-of-the-art seek-to-seek network. We also compared to Neo, which uses a CGIS approach for program synthesis. And finally, we compared to NetBeans has a plugin that actually uses handcrafted rules to do this translation. So we compared to all these, and you can see that within the 5-minute timeout, none of these tools could solve more than 20% of the benchmarks. And actually, within the first 5 seconds, our tool was able to solve more than any of these other tools could solve within the full timeout. So pretty good results for the Java Stream benchmark, and the results for the Python benchmark are almost exactly the same. Our tool can solve 80% of the benchmarks within the 5-minute timeout, and none of the other tools can exceed 20%. The final experiment that we did is we wanted to test how useful were our key innovations in this work. So in particular, how important was our cognate grammar network, and how important was our bidirectional pruning algorithm. So we performed an ablation study where we took various components of our tool and subbed them out. So for example, we would sub the CGN component of our tool out with the ASN from the literature and saw how it performed. I won't go into what exactly each of these ablations here corresponds to, but you can definitely check out the paper for a reference on that. But the overall takeaway here is that our tool with no ablations, i.e. the full tool, is the line in brown, I think, yeah, the dotted brown line at the top. So it performs the best, and none of the other ablations are even able to exceed 50%, I believe. So the conclusion here to take away is that all of the components that I've mentioned in this talk were fairly critical for good performance, at least in the benchmarks that we considered. Okay, so I'll wrap up here just to conclude with a kind of summary of what I showed today. So I presented a technique where we can take an imperative source program and automatically create a functional style equivalent program. And the two key innovations in our approach are I presented a cognate grammar network, which is a neural architecture that helps intelligently guide the search based on this observation of shared expressions. And additionally, a trace-compatibility pruning component, which is able to leverage our trace compatibility assumption to prune large parts of the search space. So with that, thank you very much, and I'm happy to take any questions.
Great. Thank you for time for questions. Hi, I had a couple questions.
Sure.
One, I wanted to know a bit more about this trace compatibility, like how you got your traces. I assume that the traces you get impact the quality of the synthesis. And then the second question was more, I guess, theoretical. Like, can you kind of characterize why these kind of snippets that you convert are likely to be traced, are these such that their stream-based one are going to be trace compatible? Can you give some kind of idea of why trace compatibility is going to be useful in the wild from a more theoretical perspective rather than just empirical?
Sure. So I think the first question, in case people didn't hear it, was about how do we actually get our traces that we're doing this pruning on. At the moment, we just generate them randomly. We generate random inputs and essentially fuzz them. In theory, we could do something smarter, I think, to get more representative traces. So I would consider this kind of a lower bound of what this could achieve. But yeah, I think there's definitely room to generate the traces in a smarter way. The second question I might need you to repeat, you were asking about why the trace compatibility assumption, like how it might be useful in other contexts. Was that the question?
Well, it just seems like the technique relies on this like trace compatibility assumption.
Mm-hmm.
I was wondering if you could give some idea of like, I don't know, among the kind of code snippets people might want to convert to string, basic APIs, why are a lot of them likely to be trace compatible?
Yeah, so I mean, the one answer is this just is kind of a pattern we noticed in practice, like empirically, in terms of why this is the case. I guess at a deeper level, you can think of like the trace compatibility assumption as representing some notion of how the code is actually computing things. And I guess there's a relationship between these functional and imperative code where they're kind of computing things in a somewhat similar way, where some of the intermediate values that they produce are the same. It's hard for me to comment on whether or not I think this would like occur in other contexts, but in this context, we've found that tends to be the case.
I'm interested in the equation results. So you basically showed that taking away any of the particular features drastically reduces the performance. My question is did you find that taking away the different features caused different benchmarks to be not solved, or did you find that there were particular benchmarks that required conjunctions of features to be able to solve?
Yes, so as I recall, it's been a little while since I've looked in that much detail, to be honest, but my recollection on the results is that by and large, it's more of a scaling issue. So the ones that don't solve tend to just be the bigger benchmarks, like the more difficult ones. I don't know if there's any kind of deeper understanding of which benchmarks don't solve.
There's also questions on that side.
I'm just curious about how well you think, because you can study government content here, which are, really big areas. How well do you be able to go across different languages? Is it, do you have to do quite a specific amount of work, or should you be generalizable?
So when you say different languages, you mean like?
Just C# say, or?
I see. I mean, so in theory, if they satisfy this kind of trace compatibility assumption, there's no reason that we couldn't apply the exact same technique. In practice, like I was kind of saying with Shankar's question, it's unclear to me in which domains this will hold and which it won't. And in the case that it doesn't hold, maybe you'd need some weaker notion. But yeah, that's definitely an interesting avenue for future work.
So you mentioned that with reference to the equation, that the 20% of benchmarks that could be solved is because the equations could be. Like, is it generally the case that the ones that could be solved are just a size issue, like if you have running domain could solve them, or is there anything you could characterize about the ones that you can synthesize easily? Is there any characteristic that makes it particularly difficult to synthesize?
Yeah, I think honestly, there's not like a terribly deep insight here, where for the most part it is just the larger programs that are difficult to synthesize. And I mean, to give a sense of like the second part of your comment, which is that like maybe you could just make the timeout longer and see. So we did experiment with like hours, and I think at one point I might have experimented with a day-long timeout, and it still couldn't solve these benchmarks. So it's not necessarily even if technically given enough time, you could solve some of these benchmarks. It gets into the realm of like the time we have left in the universe. So some of this, so for the most part, to answer your original question, it's a question of the size of programs we're considering.
Great stuff. So I was wondering, in terms of your benchmarks, since you said you could come up with new benchmarks, how do you rate the complexity of these benchmarks? Are they just a few lines of code, or what kind of grammar were you expecting to be able to synthesize across? Was it just like formulas and statements, or?
Yeah, so that's a good question. So in general, we were aiming for like kind of medium-sized benchmarks, I would say. I tried to give a sense of it with the AST nodes, but that's probably not a totally intuitive sense of the size of these actual programs. I would say the example I used in the beginning of the talk is kind of somewhat representative, if a bit on the small side, of the types of benchmarks we were considering.
let me ask a question.
Sure.
Very nice talk indeed. So in terms of the formal correctness guarantees, what can you get out of this approach? So you write one program to another one. How can you argue that they are indeed equivalent?
Yeah, so this is a good question. I mean, in practice, usually in the synthesis community, you do some form of bounded model checking, which is essentially what we do here, right? So like in a CGIS approach, you'll verify essentially that you're equivalent modulo some set of examples. And then in our technique, the verifier we use is a bounded model checker. So we only get guarantees up to some finite bound. In theory, if you had a sufficient verifier, you could plug that into our synthesizer as well. It's kind of a module of the system. So yeah, like practically for our tool, the guarantees are bounded, but in practice, there's no reason you couldn't integrate a better verifier if you wanted.
All right. Okay, thank you. Another question which probably elaborates on something that, meanwhile, is So in terms of the user effort, so imagine I want to use it for my own framework that does something nice. What exactly do I need to implement and what exactly do I need to verify about my implementation to make use of your approach?
So if I understand the question correctly, you mean if I wanted to apply this to some new domain, right?
Yeah,
Some
so
new
I need
translation.
to provide this to grammars and I also need to prove that property that you mentioned before.
Right, so that would be the first step is you need the grammars and you need to prove the property. You would also need to provide some type of verifier, right? So that when you produce a target program, you can verify that it's equivalent to the source program. You would also need, so as I mentioned, our system relies on the symbolic semantics for the language. So you need to provide those symbolic semantics.
And how large is this effort for new language?
So for ours, it's not significant. I think I have like, maybe I have an example. Sorry. So like these are the semantics we were using for our example that like can be summarized in like a table. They're not terribly complex. I mean, the more kind of precise semantics you can give, probably the better performance you're going to get. But yeah, that's I don't think the overhead is significant.
Thank you. We have time for the last question there.
Yeah, I really like this. A lot of interesting stuff here. I was just wondering, like, given that even with like data, there's something you can solve, if you could speculate on like which pieces of this are the biggest barrier to scaling it, and what might help scale it.
Right, so the biggest barrier is at the end of the day, you can guide the search more intelligently and you can prune like parts of the search space, but it's still a very large space, right? So one way you could improve things is to more intelligently search the space than our cognate grammar network. So for instance, one of the directions we're pretty interested in is since we started working in this domain, large language models have really exploded, right? And GPT-3 is very powerful. And so I suspect that we might be able to get some much stronger guidance in the search by integrating some sort of large language model. So in general, yeah, that's kind of the knobs you can turn. You can search the search space more efficiently and prune more of it. I think in this context, the former is going to be more effective because it's difficult to prune the search space safely.
All right. I think we're out of time. Let's thank Benjamin again.